Hello everyone, welcome to today's engineering mechanics lecture. In our previous classes, we learned about different types of beams, supports and support reactions and the concept of equilibrium. Today we are going to study two very important topics in beam analysis, that is shear force and bending moment. These concepts help us understand how internal forces develop inside a beam when external loads are applied. By the end of this lecture, you will be able to understand the meaning of shear force and bending moment. Follow the standard procedure to calculate them and draw both the shear force diagram and the bending moment diagram. So let us begin with the basic concepts. Let us first understand the meaning of shear forces. Whenever external loads are applied on a beam, internal forces are developed inside the beam to maintain equilibrium. One of these internal forces is called the shear force. The shear force at any section of a beam is defined as the algebraic sum of all the vertical forces acting either to the left or to the right of that section. Imagine cutting the beam at a particular point. If we observe either side of the cut and all the vertical forces, the result is called the shear force at that particular section. The figure on the right side shows the sign conversion. If the left portion moves upward or the right portion moves downward, the shear force is considered positive. If the left portion moves downward or the right portion moves upward, the shear force is considered negative. Always remember that sign conversion is very important because it determines the shape of the shear force diagram. Now let us move to the second important concept, which is the bending moment. When loads acts on a beam, they not only create a vertical forces but also produce a turning effect. This turning effect tends to bend the beam. The bending moment at any section is defined as the algebraic sum of the moments of all the forces acting either to the left or to the right of that section. To calculate the bending moment, we multiply each forces by its perpendicular distance from the section and then add all the moments together. The diagram shows here illustrate how the beam bends under loading. The upper surface experiences compression while the lower surface experiences tension. Between them lies the neutral axis, where the bending stress is zero. Understanding bending moment helps engineers design beams that can safely resist bending without a failure. Before solving any problem, we must follow a systematic procedure. The first step is to draw the isolated beam by separating it from its support. Then determine all the reaction forces and reaction moments acting at the supports. Then draw the complete free body diagram showing every external load and support reaction. In step 4, calculate the shear force at important section by adding the vertical force. Then calculate the bending moment at the same sections by taking moments. Finally, step 6, use these calculated values to draw the shear force diagram and the bending moment diagram. If you always follow these 6 steps, solving beam problem becomes much easier and more organized. Now let us solve an example. Draw the shear force and bending moment diagram for the cantilever beam shown as the figure. We are given a cantilever beam fixed at point A. Three downward points or loads are acting on the beam. A load of 3 kilonewtons acts at point B. A load of 5 kilonewton acts at point C. Finally, a 8 kilonewton load acts at the free end D. The distance are 1 meter from A to B. That is, you have to see the diagram. Our objective is to determine the support reaction, calculate the shear force and bending moment at different sections, and finally draw the corresponding diagrams. The first step to draw the free body diagram. Since the beam is fixed at point A, three reactions exist at the fixed support. These are the horizontal reaction HA, the vertical reaction VA, and the fixing moment MA. Next, we include all the applied loads exactly as shown in this problem. The distance between the loads are also marked carefully because they will be required while calculating moments. This completed free body diagram becomes the basis of applying the equations of equilibrium. Now let us calculate the reactions using the equations of equilibrium. First we apply the horizontal force equation. Since there are no horizontal external loads, the horizontal reaction HA is equal to 0. So here we have to calculate each point A, B, C and D. From sigma f of h we have to calculate the HA, that the HA is 0. Then we have to calculate the sigma f of phi, in that we have to calculate the VA, that is 16 kilonewton. Before that we have to calculate the sigma MA, in that we will get the MA is 66 kilonewton meter. Next, let us determine the shear force. We begin from the free end D. At point D, only the right kilonewton loads acts. Therefore, the shear force at D is plus 18 kilonewtons moving towards point C. We include both the 8 kilonewton and 5 kilonewton loads. Hence, the shear force becomes plus 13 kilonewtons. At point B, all three loads contributed. Therefore, the shear force becomes plus 16 kilonewtons. Finally, the shear force remains plus 16 kilonewtons at the fixed support A. These values will now be plotted in the shear force diagram. Now let us calculate the bending moment. At the free end D, so the bending moment is 0. In the free end, always the bending moment is only 0. At point C, only the 8 kilonewton load contributed. Therefore, the bending moment is minus 24 kilonewton meters. At point B, both the 8 kilonewton and 5 kilonewton loads are contributed. Hence, the bending moment becomes minus 15 kilonewtons meter. Finally, at the fixed end A, all three loads contributed. The total bending moment is minus 66 kilonewton meters. The negative sign indicates that the beam experiences arcing bending in a cantilever beam. Finally, using all the calculated values, we have to draw the diagrams. The shear force diagram consists of horizontal steps because only points loads acting on the beam. The shear force changes suddenly at each load position. The bending moment diagram starts from 0 at the free end and they gradually increase in magnitude towards the fixed end. The maximum bending moment occurs at the fixed support because it resists all the applied loads. This diagram helps engineers identify critical sections of a beam and design safe structural members. Let us summarize today's lecture. We learned the definitions of shear force and bending moment. We studied the sign conversions used for both quantities. Then we followed a systematic procedure by drawing the isolated beam, preparing the free body diagram, calculating the support reactions, determining shear force and bending moment values, and finally plotting the shear force diagram and bending moment diagram. These concepts are fundamental in structural analysis and are widely used in automotive industries, mechanical industries, and civil engineering designs. With this, we have completed the topic on shear force and bending moment. In the next lecture, we will solve some more numerical problems and different types of beams. Thank you watching this video. See you in the next class. Thank you so much.